So this week, our coverage, our topic will be on the chi-squared chapter, which is, as you can see on your screen. Do you see the Excel worksheet where I have the test of independence matrix?
Yep.
Yes.
Okay, good. So this is a continuation and extension of what we started talking about in the ANOVA chapter. That is, we're talking about tests for determining whether two variables are independent or not correlated, or in other words, you also want to see if a couple of variables are correlated, all right, or dependent. So when we started talking about these tests of independence, we talked about identifying the variables in a research question, and then classifying them according to, whether the variable is independent or the variable is dependent, and then we're able to determine what the response variable is, or what the variable of interest is. We determine its classification, whether it is qualitative or quantitative. All right. So here are some examples that you might see as application of this test of independence. For example, this is, I think we've talked about this before. The question is, does gender affect product choice? So in this question, you have two variables. The variables are product choice, and this is the response variable, right? And this is qualitative. And then the other variable, which is gender of the consumer. And gender is the factor or the independent variable. And this too is qualitative. So because the product choice, which is the dependent variable, is qualitative, and then the independent variable is gender, which is qualitative, the appropriate test is what is known as the chi-square test of independence. Okay, so in fact, in this worksheet, I've summarized the hypothesis setups. You will note that one of the uses of the chi-square distribution is this number 2 here, which talks about the independence of two categorical, or also known as qualitative, variables. All right. So this particular chi-square test can also be used for comparing proportions of two or more groups. If you recall, in chapter 10, we talked about a procedure for testing a population proportion, so meaning one population. And in chapter 11, we looked at the Z distribution, or the normal distribution, as a way to compare the proportions of two populations. But now the question is, what if you want to compare proportions of 3 or more groups? For that kind of testing, the appropriate test is known as the chi-square distribution. All right, so essentially in number 2 here, I've combined two tests of hypotheses. Okay, they're the same. Are we okay so far? All right, so here's how we set up the hypothesis for testing independence of two categorical variables. The null hypothesis says variables 1 and 2 are not dependent. In other words, we can say these two variables are independent. So when this is sort of a generic statement, so when you set up hypothesis, you would replace, variable 1 with the actual variable. So in the the in this example here, we will say that product choice and gender are independent. So what does that mean from our marketing standpoint? Well, that means that the product that you are selling does not appear more to one gender or another, right? Meaning gender really doesn't make any difference in terms of appeal for your product. The alternate hypothesis here will say that the product choice and gender are dependent or are correlated. So from a marketing standpoint, that is important to know because you can target market your product. If it is your intention to sell more to a gender group that tends to buy your product, then you can target your promotion and advertisement accordingly. All right. So that's the test for independence for the first question. How about the second one? Next question. Does age of a buyer determine how much he or she will spend on entertainment? Okay, so here the response variable Y is the amount spent by a consumer on entertainment, which is quantitative, okay? And the independent variable, the predictor variable, is the age of the consumer. And it is quantitative. So we go to this matrix. The dependent variable is quantitative. The independent variable is also quantitative. The appropriate test or procedure for testing correlation is what we call regression and correlation analysis. That is a topic that we will cover next week and the following week. All right. How about this particular question, the next one? Does gender determine how much a person will spend on entertainment? So Y, again, is the amount that a consumer will spend on entertainment, which is also quantitative. But the predictor variable is gender. Okay, so the dependent variable is quantitative, and the independent variable is qualitative. We saw that in the previous chapter, the ANOVA, right? When we compared the means of two or more groups. How about the next question? Does age of a buyer determine whether he or she will buy a product or not? Okay, so age here is the predictor variable, and it is qualitative. And the response variable is whether consumer will or won't buy your product.
Renee?
Yes?
Did you mean age in the predictor there?
Huh?
Did you mean age for the predictor there instead of gender?
Oh, yeah, thank you. Yep. Age is quantitative. Thank you for pointing that out. So we have here the dependent variable is qualitative and the predictor variable is quantitative. So here's the appropriate test. All right. You can use either logistic regression, or also known as a binary regression, or discriminant analysis. Unfortunately, this is a topic that this one is not covered in this class. So as far as our class is concerned, we're only, we've covered ANOVA before last week, and then we will be covering chi-square this week, and then regression and correlation next week, and the following week. All right, but I just needed to, include this in the discussion, because, or at least in the lecture, because there are times when you want to, your response variable is a yes/no type of question, right? So given quantitative variables, predictor variables, that if you use logistic or discriminant analysis, you'd be able to assess the probability that a person will say yes or no to, let's say, a sales call, for example. Or this is useful in recruiting. When you are recruiting customers or clients, customer clients will either say yes to you or no to you. So if you want to be able to determine the probability that the client, your prospective customer would say yes to a proposal, this would be, meaning logistic regression or discriminant analysis would be a useful tool for that kind of prediction. Okay? How about the last two? Is there a correlation between a student's final grade in 282 and the student's grade in Math 243? Meaning, for me as an instructor, could I use a student's grade in Math 243 as perhaps a predictor of the student's success in BA 282, success being measured in terms of the final grade? So the variable of interest here is final grade in BA 282, which is quantitative, and the independent variable is Math 243 grade, which is also quantitative. All right, so given both y and x are quantitative, going this way and this way, the appropriate test for determining correlation between these two variables is known as a regression and correlation analysis. Okay? All right, now how about these last two? I'll let you look at them and tell me what the y and x variables are. Who wants to take a crack at this?
So I guess I could go, the y, the response would be the final grade expected, and
Okay. Final grade expected in 282, is that right, Iridian?
Yeah.
Okay.
Yeah.
How about
And
x?
then
What is the predictor variable here?
the x would be the overall GPA of the student.
All right. Which is also quantitative. So this will require the use of regression and correlation analysis. And then finally, suppose that I want to be able to predict how well a student will perform in the second exam based on his or her exam 1 score. What's the response variable?
The exam 2 score.
Exam 2 score, okay. and X.
The student's exam 1, and they're both quantitative, which means
Uh-huh.
we're going to use the linear regression.
Correct. All right. So that gives you maybe another sort of overview of what we did in the last 2 weeks, and then what we're going to be doing in the next 3 weeks, focusing on the chi-square as well as regression and correlation chapters. All right. So we've talked about this. The chi-square distribution is, in terms of its shape, it is similar to the F distribution in that it is, right skewed, something like this. So it starts at 0, and the chi-square distribution will be like this. So like in the previous chapters, when we do hypothesis testing using the chi-square distribution, we are still going to be comparing, what we call as the computed statistic. And this time, the computed statistic is known as the chi-square statistic. So we compute, we compare the computed statistic to a critical statistic. And again, as we learned in the previous chapters, the critical statistic, which marks the boundary between 2 regions, the fail to reject HO region and reject HO region, it is based on, again, the significance level, or alpha. Okay, so that's alpha. So we can also use the p-value to reject the null hypothesis. As we have been using over and over again, we say that we will reject the null hypothesis if the p-value is less than the significance level. All right. So as far as the testing procedure is concerned, we will follow the same 5-step procedure. The only difference is in the use of the hypotheses. Are we good so far? All right. Now, one of the most common uses of the chi-square distribution is what is known as the goodness of fit test. All right. Goodness of fit test. Now, what is a goodness of fit test? Basically, a goodness of fit test, it asks the question, does a sample, so if you were given a sample, a data set, the question is, does this particular sample come from a specified or from a specific distribution? All right. If you recall or remember that in many of the problems we did in when we started hypothesis testing, especially when the sample size is small, less than 30, there was always an assumption that we made about the population, the distribution of the population where the sample is coming from. Does anybody remember what that assumption, especially for small samples?
Is that they're normally distributed?
That's right. That's right. So in statistical hypothesis testing, when we make certain assumptions, when we carry out a test, we normally have to test whether that assumption is satisfied or not. So one of the ways to test whether a sample indeed comes from a normally distributed population is by looking at, conducting what is known as a goodness of fit test. All right. Now, here's another use of goodness of fit test. All right, suppose that Doug, since he used to manufacture slot machines, right? Is that right, Doug?
Slot machine components, not the machines themselves.
Okay, so all right. Well, it's still in that field, gambling field. Suppose that Doug gives Chris a die, which he claims, he meaning Doug, as fair. All right. So the word fair here, what does that really how does that translate in terms of, probabilities? So if you have a die, how many sides does it have?
6.
6, all right? So the 6 are, correspond to the number of dots on each side, okay? So when Doug says that this particular die is fair, what does that really mean in terms of the probability of observing each of these outcomes? Meaning if you roll the die one time, what's the probability of observing a 1, assuming that this die is fair?
1 out of 6.
What? 1 out of 6?
Yeah.
Right? Okay. So the die is fair if the probability of observing each of these outcomes, if they are all equal. Okay, does that make sense? So, but Doug is claiming this die that he gives to Chris as fair. Should we trust Doug? Well, suppose that I, say, as the famous, what Ronald Reagan famously said, trust, but verify. All right, we trust Doug, but hey, we're going to verify. How do we verify Doug's claim? How do we verify Doug's claim? Should we just accept his statement as truth?
I trust him.
Chris, what did you say, Chris?
I said I trust Doug. He seems
You
trustworthy.
trust Doug.
Yeah.
I won't. Not in this case, especially if, money is at stake. Remember, I'm going to use the die to play roulette or something.
So in this case, wouldn't it be fair to roll the die a couple times, and technically you could just do a hypothesis test on whether or not there's a difference in what should be average and what isn't?
Yeah, okay. So you said roll the die a couple of times, all right? Yeah,
Well, maybe-
true. I mean, that's one way is to do when you say a couple of times, really we're talking about generating a sample, right? Rolling a die X number of times, and then out of that roll, you observe. So you will observe here. Observed frequency. And we will have expected frequency. So let's just say that based on what we learned in chapter 10, when we talked about estimating sample size, minimum sample size to estimate the probabilities, let's just say that the sample you have determined is 300. Okay, I'm just throwing this number out there. So that means that Chris will roll this die 300 times. And every time he rolls the die, he will take note of how many ones appear, twos, threes, and so on and so forth, right? So that would be what we call as the observed frequency. So let's just say that Chris has, a spare time today and really tested this die, and he observed first, for one, he observed it to appear 50 times, 2 appeared 45 times, 3 appeared 47 times, 4 appeared 54 times, and then 5 appeared 40 times. And I'm going to cheat here a little bit because I want to make sure that the sum of the frequencies here is equal to 300, right? After all, we're rolling this die 300 times. So what's missing here is, what would be this? This would be 54, right?
64.
54, right. So these are the numbers what we call as observed
It should be a
frequencies.
64.
I'm sorry?
It should be a 64.
Oh, 64, thank you, yeah. Yeah, I should have picked that up too because 64. All right. So these are based on the sample. Now recall that I think at one time I talked about that when we compute a test statistic, it is really based on the source of the variation between what we observe against what we expect. For example, in testing the mean of a population, what we observe is X bar, which is what we obtain from a sample, and then the expected value is the hypothesized mean. So in any kind of hypothesis testing, which is also true in chi-square analysis, we are really trying to understand what the source of this error, sampling error is. All right. Is the source random? Or is the source really more systematic? Meaning something that can be explained. Okay? So in our hypothesis testing, when we reject the null hypothesis, anytime we reject the null hypothesis, what we are really saying is that the source of the variation between what we observe and what we expect is something that is more systematic, meaning we can explain it. On the other hand, if the null hypothesis is not rejected, what we are saying is that the difference we are observing between X bar, or P, in comparison to the parameter of interest, that the source is mainly random, meaning there's really nothing, to explain. It just happens because of the randomness of the experiment. Okay? So going back here. So we will relate that to this, the observed are these numbers. So if the die is really fair, what is the expected number of ones? Again, this assumes that the die is fair. If the die is fair, out of 300 rolls of that die, how many are we expecting to appear as 1? How many are expected to appear as 2, and so on and so forth? What is the expected
My die is
value?
guaranteed to give you 50 each time, so that's your expected.
Okay, how did you arrive at that 50, Doug?
I took the probability 0.16667 times my sample size 300.
Okay, right. So basically the expected value is a product of the probability and the random variable. All right, so if the die is fair, then the expected number of ones is 50, and then that will be true for 1, 2, all the way to 6, right? Based on this probability. So in this column, you have the expected values. Now let's look at the differences in the observed minus the expected frequencies. What's the difference there? Okay.
0.
0, and then, okay. So this is something that we ask ourselves. How likely is it to observe, 10 less 5s? Or how likely is it to observe 14 more 6s when you roll this die 300 times? Okay, is this something maybe a random occurrence, these two? Or is it something that is more systematic about the die, meaning really maybe the die is rigged to favor certain numbers or not favor certain numbers? Okay, so to answer that question in a more objective and scientific way, we carry out a test. All right, so this one would be a good use of this goodness of fit test. So the null hypothesis would say, let me copy this. The null hypothesis would say, all right, and instead of saying a specified distribution, we will call this, before I do that, if I plotted this probability of X on the Y-axis and X on the vertical axis, the horizontal axis, the graph would look something like this. Okay, so here's X, 1, 2, 3, 4, 5, 6. And here's P of X, the probability of each X. The probability of each X is 1/6. All right. So 1 will have a bar that goes that way, 2, 3, 4, 5, 6. Okay. Do you recognize that shape? What distribution? We've talked about that kind of distribution.
The unit distribution?
What, so say that again, Aridan?
The unit distribution?
The unit, did you say unit?
Yes.
Not unit, uniform distribution. Okay, I think we talked about that in the continuous probability distributions, where the shape of the distribution is rectangular. Okay. So the alternate hypothesis will say does not come from a uniform distribution. And then it says we will reject HO if the chi-square, the computed chi-square, is greater than the critical chi-square value. Okay, so let me just, I'm going to show you this formula and compute it. You don't have to really memorize this, but I just want to show you this formula so that you can appreciate, being able to answer the question whether the sampling error is systematic or random. Okay, so here's the formula. It says we will compute the difference between the observed and the expected, and then square that difference. Okay, so here I'm going to just write O minus E squared. This is just a label. So where's my O? O minus E. We already computed that to be this, right? And square. And we'll copy this. Okay, and in this next column, I'm going to divide that squared difference by the expected frequency. So I'm just going to write this O minus E squared divided by E. So that would be this cell divided by the expected frequency. All right, so that's still 0. And copy this down. So these numbers that you're observing here, these are the, oh no, sorry. I was referring to the wrong cell. I said E, but I'm referring to, D. I should be referring to this cell here, which is E5. All right, that's more like it. So these numbers represent the O minus E squared divided by E. And then what we need to do is to sum up all these numbers. So we'll just say sum of that. So this is what we call as the computed chi-square statistic. So for the computed chi-square statistic, we will compare that to a critical statistic. Okay, so here's how we compute the critical statistic, which is based on, so the critical statistic is using the chi-square, chi-square.ind. Okay. So the chi-square that inverse asks for the probability. Okay. What's the probability? 0.05, comma, degrees of freedom. Degrees of freedom is k minus 1. All right. K, where k is the number of categories. So we have six categories. Minus 1 is 5. Oh, okay. Now this one is, this has got to be a right-tailed test. Okay, so instead of 0.05, this should be 0.95. Okay, so let's draw our distribution. The distribution shows this. This is 0.05. The critical chi-square is 11.0705. And the computed statistic is here, 6.606. It is inside the fail to reject HO. And by failing to reject HO, the null hypothesis, we're saying that, we're concluding that the sample, meaning this number here, comes from a uniform distribution. Okay, translation. The die that Doug gave Chris appears to be fair. We don't have any evidence to say otherwise. Okay, so let's go back to this number here. Remember I asked earlier, is this number large enough for us to say that the die is not favoring this number? Is this large enough for us to say that the die is favoring more this number? the answer to that question based on our test is no. These are what we will call random occurrences. Okay? Meaning, if we ask another person to roll the die, same die, these observed numbers will not be the same, but perhaps, these numbers will be a lot different. Okay? So is that clear? Does that make, okay, good. All right. So let's look at here, this problem. There are 4 entrances to the government center building in downtown Philadelphia. The building maintenance supervisor would like to know if the entrances are equally utilized. All right. To investigate, 400 people were observed entering the building. The number using each entrance is reported on this table. At the 0.01 significance level, is there a difference in the use of the 4 entrances? So the null hypothesis how would we state the null hypothesis?
That each of the entrances are equally utilized in general.
Mm-hmm. By the people entering the building, right? Or translation in a more technical term, the distribution is uniform. Okay? The alternate hypothesis would say that the utilization of the 4 entrances is not equal among them. In other words, the distribution is not uniform. Okay? So that's how we will set up a hypothesis. Now, for this problem, instead of solving it this way, the die example, we're going to just use the template to do the calculation for both the computed statistic as well as the critical statistic. Okay, so this is an example of a goodness of fit test. All right, so let me open the template. Okay, there you go. Do you see the template on your screen?
Yes.
Okay, thanks. All right, so the chi-square applications can be found down after the ANOVA. Oh, before the ANOVA. Okay, so here you go. We will be using the goodness of fit test. And so here's my data. Here's main. We'll just type in the information, Rod, Sherry, and Walnut. All right. So we input here the relative frequency. The relative frequency is the probability of each x. So what number should I put in here?
0.25.
0.25, okay. So that would be equal to 1 divided by 4. And make sure that the sum, if you are going to input the information here manually, that it adds up to 100%, okay? The observed frequencies are 140, 120, 90, and 50. So here's the output. The computed chi-square. What's a computed chi-square equal to?
Is it 46?
All right, 46 over here. Good. And the critical?
6.251.
Which is 6.251. And we will note that in this distribution, the computed statistic over here is way inside the rejection region. In fact, if we look at the p-value, it's quite small, which means the p-value is equal to almost 0, which means that that we have extremely strong evidence to support the alternate hypothesis. Okay? So from, if you were the building manager here, and if you were to decide, say, because of this COVID thing, most buildings are now, they're using one door for entrance and another door for exit. Which of the doors will you use as entrance and exit? Obviously, you would pick Main Street, perhaps the entrance, and maybe the Broad Street as exit based on the frequency. Okay? Does that make sense?
Yep.
All right. All right, so I'm going to let you do this on your own. 1725. The owner of a mail order catalog would like to compare her sales with the geographic distribution of the population. According to the U.S. Bureau of the Census, 21% of the population lives in the Northeast, 24% in the Midwest, 35% in the South, and 20% in the West. All right, so listed below is a breakdown of a sample of 400 orders, randomly selected from those shipped last month. So the question is, at the 0.01 significance level, does the distribution of the orders reflect the population? So this is a typical marketing example where sometimes you would want to see if a particular market, for example, a local market, would fit the national profile. Because if it does, maybe you can use this local market as your test market. That whatever you find in this test market, you can say it will be applicable if you go nationwide. All right? So, how would you set up the null hypothesis? you can use words to describe the null hypothesis. So Chris, how many participants do we have?
400.
Oh, no, I mean participants in today's session.
We currently have 11.
11, okay, so under, huh? Did you say
Well,
over earlier?
We started with, I think, 15 or 16. But yeah,
15 or
Mine says 13.
Oh, really? Okay, yeah, I got 13 including Doug and I.
right.
So
We're up
there's
to
actually
17
11 out of the 20,
Lost a couple.
20 students. Okay, how would we set up the hypothesis?
Would it be her sales?
The what?
Would it be her sales with the geographic distribution of the population?
Okay. The what?
Her sales with the geographic distribution of the population.
Okay, the sales or the order, the
Yeah.
distribution. So yeah, the distribution of who is this? It doesn't say. Oh, okay. Of the mail order catalog follows the national population distribution, right? And then the alternate hypothesis would be that the distribution does not follow. So once again, we can use the goodness of fit test to see if the distribution, if you look at, well, it's really not easy to compare at this point, right? So let's look at over here. So the regions are Northeast, Midwest, South, and West. The relative frequencies. So what should I be putting in the relative frequencies here? The observed frequencies are 68, 104, 155, and 73. What's missing here?
The national ones listed in the problem.
Okay, so which ones are those, Aridian?
0.21, 0.24, 0.35, and 0.2.
Okay, good. So that would be this 0.21, 0.24, 0.35, and 0.2. Okay, what was that again? 0.21?
0.21, 0.24, 0.35, 0.20.
0.20, okay. And of course, they add up to 100%, so the numbers are very likely correct, the way I inputted them here. All right, so here's the output.
You were supposed to change the significance level to 0.01.
Oh, 0.01, okay. All right, so that what will if I change the significance level to 0.01, what will be affected in here?
The critical value?
The critical value, correct. All right, but you know, at this point, really, we can simply look at if you look at the p-value, look at the p-value. It's quite high. So even at alpha 0.05 or alpha 0.01, you will still fail to reject HO, and also here, fail to reject HO. Right? So by failing to reject the null hypothesis, what can we tell this owner of the mail order catalog in terms of the distribution of the orders of shipment last month? Does it follow the national population distribution or not?
It does follow.
Right, because we will fail to reject the null hypothesis. So we are saying that the distribution of the mail order catalog follows the national population distribution. All right, are we good?
Yep.
How about 1726? Let me make this bigger. Banner Mattress and Furniture Company wishes to study the number of credit applications received per day for the last 300 days. Okay, the sample information is reported over here. So number of days where there were zero applications received, 50 of the 300 days. Number of days where only one application was received, 77. All right, so this sum here, this should add up to 300. Would it be reasonable to conclude that the population distribution is Poisson with a mean of 2? Okay, remember when we started chapter 5, I believe, or chapter 6, when we talked about discrete probability distributions? Poisson distribution was one of the distributions we studied, and we said the Poisson distribution is one where we use to estimate probabilities of expecting number of occurrences within an interval. So in this case, we're talking about, number of applications received in each day. So we are asked to see if this distribution follows that type of distribution with a mean of 2.0. Okay? So we will state the null hypothesis this way. HO, the number of applications received per day follows the Poisson distribution with mean of 2 applications. Okay. The alternate hypothesis would say that the number of applications received per day does not follow the Poisson distribution with a mean of 2 applications. Okay. So I'm just gonna rewrite this part here, over here. X number of applications, 0, 1, 2, 3, 4, and then 5 or more. So that's X. And the number of observed frequencies. Okay, so we will say here's the observed frequencies. Are 50, 77, 81, 48, 31, and 13. Okay, let's confirm if my numbers are correct. Sum this up. Okay, 300. So what is missing in this table?
The relative frequency?
Okay, so the probability of each X. How do we compute the probability that X is equal to 0 of a Poisson distribution when the mean is 2? We don't have to do that by hand. We can go back to the template. So here's the Poisson distribution. Okay. What is the mean? 2, right? So this table actually will give us the probabilities. I'm going to just copy these. In fact, let me move this over here. So let me move it some more. Okay. So fill in the blank here. Here's the table. What's the probability that X is equal to 0?
Zero 0.1353.
All right, Doug, where are you picking that number from?
The probability of X in the table over to the right there.
Okay, over here, correct, right? So this one is 0.1353, and then 0.2707, and then 0.2707. 3 is 0.1804. 4 is 0.0902. And then 5 or more. The 5 or more, we will have to, the long method would be to add all these numbers up. The shorter way would be to what?
Use the complement rule and do 1 minus the sum of all the prior probabilities.
All right. Okay. So if we added that column of probabilities, that is equal to 1 or 100%. So we will be using these probabilities and these observed frequencies in the template. We'll go back to the chi-square goodness of fit test. I'll paste that here. All right, so 0, 1, 2, 3, 4, 5 or more. Relative frequencies are 0.1353, 0.2707, 0.2707, 0.1804, 0.0902, and 0.0527. The frequencies are 50, 77, 81, 48, 31, 13. So we'll paste that over here. Look at the p-value. Okay. Therefore, we will fail to reject the null hypothesis. And by failing to reject the null hypothesis, if we go back to our hypothesis setup here, that we will say that we cannot reject, well, at this point, we will say that the number of applications, credit applications received per day follows the Poisson distribution. Okay, are there any questions? Are we good so far? All right. So I think today I'm just going to give you guys a break because we have only, this many problems to do for the next session. So I'm going to stop here. And so for the next session, we're going to look at the problems involving test of independence of two categorical variables. Okay, so I just kind of give you with a quick example here. Well, maybe not that one. Yeah, here's a good example. Is there a relationship between the opinions of voters or citizens when it comes to this idea of government reducing the deficit? Is there a difference between, these two groups? Meaning, does one group favor one option over another? Okay, so we note here that in this example, there are two variables. Again, so we're not going to solve this. I just want to set this up in preparation for next session. So here, the response variable is opinion on the reduction of the deficit. And X is gender. Okay, so this is kind of a question that maybe politicians would like to know, because they would want to see if, whether a particular group would favor one over another, and that kind of helps them shape their message, assuming that there is a correlation between gender and opinion on the deficit. So we'll continue with this problem in the next session.